Alright, we're going to take a look at nuclear stability. So the question is, what makes a nucleus stable or unstable? What makes one nucleus radioactive but another one not radioactive? Why does a particular element undergo alpha decay but this other one undergoes beta decay? What makes an element radioactive? And so to think about that, we need to look at kind of the interactions that are going on inside the nucleus again. So remember the nucleus, protons and neutrons. And they're all packed in there really tightly, and they're held together by that strong nuclear force. And so we've got the protons, which are positive, and the neutrons, which are neutral. So in a nucleus like this one, you've got the protons and you've got the neutrons. Those protons that are both positive, like those two right there or those two right there, are really close to each other, which means there's going to be some repulsion force there with those like charges pushing against each other. These neutrons right here, so they're going to have that strong nuclear force pulling them together, but there's not going to be any force pushing them away. But these two protons, or those two protons, or those two, or even those two right there, there's going to be some repulsion going on, but there's also going to be that strong nuclear force that holds them into place. So the protons are providing repulsion, but they're also providing some of that nuclear force that's holding them together. The neutrons, no repulsion, but extra attractive force, extra nuclear force. So the neutrons serve the purpose of helping pull this atom together. If we didn't have those neutrons in there, the nuclear force from just the protons wouldn't be enough to hold this entire nucleus together. So those neutrons are kind of mediators. They make it so that this nucleus can stay together because they provide that strong nuclear force with no repulsion. So we need a ratio of protons and neutrons together in order to make a nucleus stable. If we have too many neutrons that are in there, so they're not really necessary to overcome any particular repulsive force, it just gets too crowded inside here. So you can have too many neutrons, or you can have too many protons, and you can have just too much of everything. That's why if you look on the periodic table, all elements above lead are mostly radioactive. And that's because they're just so huge, so massive, that they can't really hold together, and so they do decay. Some decay faster than others because they're really repulsive to each other. Other ones much, much slower because it's just maybe a little too crowded in there. So when elements undergo decay, they could do something like an alpha decay. And an alpha decay means two protons and two neutrons slip off. So let's take those, and they would be emitted off in the form of an alpha particle. And so that would be 4 and 2. And then they're gone. So this is going to change the identity of the element. It's also going to change the size of the nucleus. And so it's going to reduce that and bring it closer to stability. Let's say now there's too many protons. And if that's the case, one of the protons is either going to have to undergo electron capture or beta positive decay. So let's say a positron is emitted. And so this proton up here, we're going to say that it loses its positive charge and becomes neutral. And when that happens, it's going to emit that positron. And these kind of decays will keep happening step at a time. Lose an alpha, lose a positron, lose a beta, capture an electron, and they'll happen over and over again, multiple decays, until it reaches the point of stability. So this particular element that we're looking at right here, this drawing, it's a small element. If we deal with the larger elements, uranium, plutonium, things like that, very, very large ones, all of them will undergo this series of decays, or radioactive series, until they achieve stability. And stability for all elements, all the heavyweight elements on the periodic table, ends at lead 208. So those elements, those high ones up on the periodic table, the ones above 82, so 83 and up, are going to decay through one of the 4 choices until they reach lead 208. Lead 208 is the first stable element on the periodic table. And not just lead in general, lead 209 or lead 206. Those would be unstable versions of lead, and even lead can decay to get to lead 208. So let's take a look now at how we can tell what kind of decay a particular element is going to undergo, or if it's stable already. So here we see a chart that matches up the number of neutrons versus the number of protons. So if we look at a particular element like zirconium right here, zirconium has 40 protons and 50 neutrons for a total of 90 nucleons. And so if we were just to graph that, that's 40 protons, so we would come up. And it's got 50 neutrons, so we would go over, and we would mark its place on here. And we can see that it falls within this kind of orangish line, and that line, that zone, is called the zone of stability. So all elements that would graph and fall in that point, when you look at their neutrons versus protons, all elements that fall somewhere in this zone are stable. So they're happy, they've got the right ratio of protons to neutrons, and everyone is set. If we come out of that zone, so let's say that zirconium has now 60 neutrons instead of 50. So it would be still 40 protons, but now it's got 60 neutrons, and so it's going to fall out here. See how that zirconium falls out of the band of stability? The zone of stability? That means that zirconium will be radioactive. It's going to have to undergo some kind of decay so that it can reduce its number of neutrons and fall back into that zone of stability. And as long as it's somewhere in this range, so even if it has, 45 neutrons, it's still going to fall in that zone of stability. So it's not like it has to be an exact pinpoint. Other elements, bismuth up here, bismuth 209, falls inside the zone of stability. And what you need to notice is this ratio of protons, or protons to neutrons. So, right here it's 1.25 to 1, and 1.52 to 1 up here. So as we increase, you need more and more neutrons in order to overcome the repulsive force of those protons. So at first, these really, really low elements, we can see the 1-to-1 ratio is all it needs. So just one proton for every one neutron in order to be stable. But once we get to about element 20, now it's going to need about 1.25 to 1. And once we get up to around element, it looks like about element 70, we start needing 1.5 for every one. So those protons, you get more and more protons, they need more and more neutrons to help bind it all together. And once you get up to about this point right here, so that's about element number 83, once you break that point, all of these elements out here in this zone are naturally radioactive. And so they're going to have to decay in order to get into that zone of stability. And they will do this by any means necessary, one of those 4 forms of decay to get them down into there. Once they get into there, that zone of stability, then they're set. And so where that zone starts right there, that would be around lead 208 that I was talking about. So the question is, you got too many protons, you got too many neutrons, or just too much stuff? What kind of decay are we going to undergo? For that answer, we need to look at the next slide. And here it is, the colored chart of stability. So not only do we have that zone of stability still drawn in right there, we also have the green zone, the blue zone, and the yellow zone, which indicate if the elements fall into that particular area, what kind of decay they're going to have to undergo in order to achieve stability. So we talked a little bit ago about zirconium, and if zirconium had 40 protons and 60 neutrons, it's going to be up there, so that would be zirconium. And so that one would weigh 100, and it would have 40 as its number. And so if it does that, you can see that it's unstable because it's no longer in that zone of stability, and it's unstable because it has too many nucleons, so too many neutrons. And if we've got too many neutrons, well, we got to get rid of some. And what better way to do that than with a beta decay? So remember, a beta decay is a neutron losing its negative charge and turning into a proton. So if we do that, it will shift the element over and drop it down. So it'll add one more and drop it down, and so it'll then fall into the zone of stability. So zirconium would undergo beta decay. It would change the element into niobium. And so that means that new element that falls into the zone of stability would be Nb, which would have an atomic number of 41, and it would still weigh about 100. And we can look on this bottom end of the chart. So down here, that means it has too many protons but not enough neutrons. And so it's going to have to undergo positron or electron capture because both of those will turn a proton into a neutron. And when that happens, it will bump it up and over and eventually get it to the zone of stability. And then out in this area, well, we just got too much of everything. And so if it falls outside here, it's going to lose protons and neutrons, both 2 protons, 2 neutrons, until it gets to this zone of stability. So, in a nutshell, chart free, beta decay occurs in isotopes that have too many neutrons. So you've got a bunch of neutrons and They don't really serve any purpose, they're just taking up a room, and so it's going to undergo beta decay to get rid of some of those neutrons. If you have too many protons, on the other hand, so too much positive charge and not enough binding force from those neutrons, you're going to end up with a positron emission or an electron capture. Either one of those will help get rid of protons. And then last thing, if we have too much of everything, so it's just too darn crowded inside that nucleus, it's going to dump 2 protons, 2 neutrons in the form of an alpha decay. And this occurs in most elements that are higher than 83 protons, so elements above lead, so bismuth and above are all naturally radioactive just because they got too much stuff. Do you remember when in quantum numbers we were talking about electrons, and we said that if you have an orbital, something like 2p, there's going to be 2 electrons that can occupy that region. And when they're in there, remember how we said one spins one direction, the other one spins the other direction? That same thing applies to the nucleus. So the reason they spin opposite directions like that, or have this opposite spin that we talk about, what that does for those 2 electrons is they're occupying a very, very small region right here, and this makes it so that strong force, that binding force, can actually hold them together a little bit better. So it helps kind of lessen the repulsive force, if you will. So having those 2 right there kind of cancels out a little bit of the repulsion, and so they can cohabitate. So electrons are actually happier when they have a partner like that to kind of cancel them out. Same thing goes for protons and neutrons. So if we have 2 protons in a nucleus, they're going to have that repulsive force that's kind of pushing them away. One way that they alleviate that is one will spin kind of the same thing. So we'll say one spins in the up and one spins in the down. What that does then is it helps to kind of cancel out some of that repulsive force, and then so those 2 protons right there wouldn't repel quite as much. Same thing can happen with 2 neutrons. Okay. If you've got 2 neutrons sitting like that, they're going to spin in quote-unquote opposite directions, and that's going to kind of help draw them together a little bit better. So it's actually going to build up that nuclear force that they provide, that strong force. So what this means is that all protons and all neutrons need to have a partner to match up with. So if we have a proton that's by itself with no other protons spinning in the opposite direction, it doesn't mean it can really have that binding force. There's nothing really for it to stick to. So in order to be stable, the rule number 1, so the most stable elements are ones with a nucleus that has an even number of both protons and neutrons. So every proton has a partner and every neutron has a partner. So if you look at the nucleons, if we look at the nucleus, if there's an even number of protons and an even number of neutrons, those elements are going to be more stable, the most stable. It's all relative. It doesn't mean that if you have even and even that it's perfectly stable and never going to decay. It just, if you have the same element that has an unmatched, it's going to be less radioactive than the unmatched partner. The second most stable version is going to be something that has an even number of protons or neutrons, but an odd number of the other. So like this little setup right here, we have an even number of neutrons, but an odd number of protons. And so this would be less stable than something that had both protons and neutrons even. And then the least stable would be something that has an odd number of both protons and neutrons, so odd and odd. In essence, what this does is it requires less energy of the neutrons and the protons. So if you have spinning in opposite directions, those 2 forces are going to sum up to something less than if they were spinning in the same direction, or if there was nothing spinning against it. And so less energy means that less effort's required, which means it's happier. So anything we can do to require less energy of atoms is going to make them a lot happier and a lot more stable. So having these opposite directions, they kind of sum up to a lower amount of energy, and less energy means more happy. Ladies and gentlemen, I present to you the magic numbers. These numbers are 2, 8, 20, 28, 50, 82, and 126. What these numbers mean in the nucleus is that if you have one of these numbers of protons or neutrons, so if you've got 20 or 50 or 2 or 8 protons or neutrons, those elements will be very stable, which means they will have a long half-life, which means they'll take a very, very long time to decay. They'll be very slow about it because they're mostly happy. And here's the really cool thing. If you have a magic number of both protons and neutrons. That's right, protons and neutrons, meaning magic numbers. Those elements will never decay. Read my lips, never decay. They can't because they're so stable, because they have magic numbers of protons and neutrons. That means the perfect ratio to where they just won't decay. These would be elements like helium-4. Helium-4 has 2 protons, 2 neutrons. Oxygen-16, that has 8 and 8. And of course, how could we forget, if we have an element that has 82 protons and 126 neutrons, that would be the element of lead, and it would have 208 as its mass. So there's lead 208. You remember how I said all those heavy elements decay until they get to lead 208? That's because lead 208 meets the magic numbers and will never decay. It has 82 protons, 126 neutrons. It's perfect. And I better just tell you the truth before you find it out somewhere else. Not all magic numbers are true. Sorry, guys. An element like 10100, which has 50 protons and 50 neutrons, it's not stable. It actually decays in a very, very short time, so it's really radioactive. But other than that tricky old 10 getting in our way, all the other elements that meet these magic numbers are very, very stable, or if they have both magic numbers, are extremely stable and will never decay. Okay, let's think back to half-life. We talked about this in the kinetics unit. Half-life is the time it takes for a particular reactant to decay by half or to react by half. When we talk about a nuclear half-life, nuclear isn't really a reaction. When we talk about a nuclear reaction, that's something completely different. So a nuclear decay half-life is the time that it takes for half of a sample to decay. So if we start off with, 100 grams of uranium, it's the time that it takes for it to decay to 50 grams. And that's the time half-life. And then that same amount of time would be what it takes to get down to 25 grams, then 12.5, and so on and so forth until it's all gone. So it's the time it takes for it to decay by half. Since this is not a reaction, this isn't a reaction, temperature does not affect it. It's all happening internally, and if you heat up or cool down a radioactive material, it is not going to change how fast or slow it decays. Half-lives also are a good indicator of how radioactive something is. Something that's extremely radioactive, something that's extremely unstable, is going to have a very short half-life. So this time that it takes for it to decay by half is going to be very, very small. Something that's more stable, so if it has an even number of protons, even number of neutrons, or one magic number, it's going to have a very, very long half-life. And that time can be everything from, hafnium, which has a half-life of 0.002 seconds. So if we had 100 grams, half of it would decay in 0.002 seconds. Or something like uranium-238, even. That has a half-life of 4.5 billion years. And so it's very characteristic of the element, and it doesn't change with temperature. And then we can use our whole half-life equation. Since all nuclear decay rates are first order, there's nothing really dependent on it except the one thing. Since it's only dependent on that, it'd be the half-life, the integrated half-life equation. And so if you remember, we shorten that down as well to T1/2 equals 0.693 divided by its rate constant. Also, since it's not temperature dependent, so it can be hot, it can be cold, it doesn't really matter, it's not going to change its rate, that means nuclear decay is very, very precise. Its half-life will not change with anything. So we actually use radioactive decay to set a lot of clocks, since it's so dependent on just its own concentration. We can use it to set time for clocks. If you've ever heard of nuclear clocks, that's what they're talking about. Carbon-14, which is carbon dating. The reason we can use carbon-14 to date things, see how old they are, is because we know exactly how long it takes carbon-14 to decay. It's not temperature dependent, so even if it was freezing and burning hot in the area where this item died, we can track how much of it has decayed, trace that back to figure out how long it would have taken it. So, if we knew that it started with 100 grams and it's left with, 0.5 grams, how long did it take to go from there to there? And we could use half-lives to trace that back and figure it out pretty simply. So this kind of very, very precise nature of nuclear decay and its half-life is really good for timing things and tracing how long it's taken certain things to happen.